Now let's talk about Docker images. So I'm going to explain the difference between a container and an image. I'm going to explain what is a layer, and I'm going to explain what are the different namespaces for images. And this is not about the kernel namespaces, which are one of the low-level components of containers. This is about like Ubuntu versus jpetazzo/clock versus myregistry.com/ etc. I will also talk about image tags. So an image, technically, it's a bunch of files and some metadata. And these files are just the root file system of my container. Now this metadata is a bunch of information that is either purely, I would say, almost aesthetics, like who wrote that image and when and why. And then some more live metadata, like which command should be executed in that container when we start it, which environment variable should be set, which UID should be used when starting that container. The images are broken down in layers, and each layer can be thought of like a code commit. So each layer can add, remove, or change a bunch of files, and it can add, remove, or change a bunch of metadata information. Images can share layers, and that's a pretty useful thing. Let's look at a fictitious Java application. I will have typically, and let's say I'm building that on top of CentOS. I'm going to have a CentOS base layer. Then I'm saying, okay, my IT department or me decided I wanted a bunch of extra things on top of CentOS. Like maybe I always want to have Emacs and VI. Not a good idea in a container, but let's pretend. GDB, a few things like that. Then this is a Java application, so I need a JVM. Then since it's in Tomcat, I need Tomcat itself. Then my application might have a bunch of dependencies and jar files, so I'm going to add that. Then I have the code for my application, and then some configuration information for my application. This is an arbitrary breakdown, but it's a fairly reasonable one. And those layers will have very different size. For instance, the CentOS layer might be, 100 megs. The packages that I added on top of that, maybe 10 megs, maybe another 100 megs. The JVM, I'm gonna say something between 20 and 50 megs. It's been a while since I haven't looked exactly at that. Tomcat, a few megs. Dependencies for my application and the application itself, like a bunch of megs. And the configuration, however, is going to be pretty small, maybe a few kilobytes. The point of having these different layers is that layers can be shared and reused between different images and containers. So that means that when I have this container, when I have a container running this image, if I want to run another container that just has a different version of the application but built on top of the same base, etc., I can reuse all those things here. Like all those layers can be exactly the same between the two containers. It's a different version of the code, so the last two layers are going to be different, but those layers can be the same. I won't have to have them in duplicate on disk. I won't have to transfer them in duplicate when I download the container image. And depending on the parameters of my runtime, I can even save some disk I/O and some caching memory by having those layers only once in memory. Same thing if let's say I operate a SaaS, a software as a service, and I have 100 customers and they all use the same version of my application but with different configuration, then that's even better because all these layers here can be identical for all my customers and just the application configuration can be different. Okay, so that's why we have layers. Now, what exactly is the difference between a container and an image? That's a little bit pedantic. An image is a read-only file system. You cannot change an image. It's immutable. It's like carved in stone. A container is an encapsulated set of processes running a read-write copy of that file system. So what that really means is that when I have an image and I want to do a Docker run on that image, I'm making a copy of that image, and that copy I can change and modify and everything. And then I run containers as a bunch of processes in a special environment. And if you're curious about those details, the keywords are cgroups and namespaces, etc. And that's a container. So a container, it's just a bunch of processes running in that environment. And if that confused you, I'm going to show something that I hope will kind of clear that up a little bit. I'm going to just run, let's say, an Nginx container and also a Tomcat container. No, not Tomcat, let's say another Nginx container. Now if I do docker ps faux, ps faux, and I'm going to unzoom that a little bit. Somewhere in my process tree, I have the Docker engine here, and if I look a little bit below, I will see here a bunch of processes that are my first Nginx container, and this is my second Nginx container. And what's interesting is that you can see the Nginx process from the host. The Nginx running in my container, that's a normal process running on my host. And from my host, I can see that process. It looks perfectly normal. I can use a bunch of tools like GDB, strace, LSOF, even PS, etc. And I can interact with those processes from the host. So the processes in my container are just normal processes on the host, but with a bunch of kind of red tape and other mechanisms around to limit what they can do and to put them in that containerized environment. That's a big difference with a VM, where for a VM I would just have one big opaque process, and it's like, oh, this is my VM. What's in it? I don't know. I mean, I could if I analyze the memory, etc., but it's not transparent. So a container is an encapsulated set of processes running in a read-write copy of that file system. I hope that sentence now makes more sense. If I had to copy the image each time I start the container, that would be a little bit slow, especially if I have a 5 gigabytes image. Like each time I do Docker run, if I need to make a copy of those 5 gigabytes, that wouldn't be great. So the container engine is using copy on write, which is a mechanism where you have only one read-only version of the image, and then there is a special mechanism. If you're not familiar with copy and write, one of my favorite metaphors is tracing paper. Like this would be my image, and then when I run a container, I put some transparent tracing paper on top, and I can draw on that tracing paper, but then I can also remove the tracing paper and the original is still here behind. So that's what the copy and write file system is doing. And that way, when I need a new container, I just put a new sheet of tracing paper and I'm good to go. A few other metaphors to explain that. We can imagine that images are like templates and you can stencil them on a wall. Since I'm a developer, I like the metaphor of object-oriented programming, where conceptually an image is a little bit like a class, and layers are conceptually close to inheritance. So each time I add a layer, I'm making a derived class that is based on a base class and can add or change methods and fields, and containers are like instances of these classes. So if you've been following closely, I said, okay, an image is read-only, you can never change an image. So how do I change an image? Like, how do I make a new image anyway? Because I want to install my stuff in an image. The answer is you don't. You have to create a new image, and to create a new image, you take an existing container and you can say, I want to transform that container in an image. So I want to kind of, I freeze it, I commit it into a new image. Okay, so to create an image, I'm freezing an existing container. But to create a container, I have to run an image, which is created by freezing a container. So I have a kind of chicken and egg problem here. So how do we break out of that? There are a few ways to do that. First, there is a special image called Scratch. And it's called Scratch because we will soon see that when we write Docker files, when we indicate a base image, there is a keyword, it's from. So when you want to use an empty image, it becomes from Scratch. So, okay. So that's one way to kind of bootstrap the whole process. There is also a special command called Docker import. And Docker import lets you provide a tarball of a file system, and it creates a container image from that. This is if you want to, I think it's called lift and shift. It's a fancy way to say you're taking an existing server and you're kind of dumping it in a container to pretend that it's a container and everything is fine. So you use tar to create a tarball of the whole file system of the server, and then you put that in a container image. There are some good use cases for that, but as I said, Casey West has an amazing presentation where he said one of the I think it's something like the 5 stage of microservices or something like that, and one of them is bargaining, where we put that monolithic thing in a container and we called it a microservice, but that's not what microservices are about. You can't really do that. I mean, you can do it, but calling that a microservice is a little bit of a stretch. But there are some really good use cases for that, and in particular for people who are like, okay, we have identified that we want to go like full on containers and everything, and we know how to do that, but we have a bunch of old applications that we are not really maintaining anymore. They just run fine. We want to keep them running, but they're not going to get updates or anything, and we still want to put them in containers, but there is no way that we're gonna spend hours, days, weeks to rewrite them or whatever in containers. Well, then that's a good use case. You can take an existing server and put that in a container, and now it shows up as a container on your platform, and that's great. Another use case that AJ might be able to tell you about is when you have really big images and you want to load those images really quick because you want to optimize the start time of your machines. Docker import will be one of the fastest ways to load an image into the Docker engine. Okay. Now, the way we are going to create images is either with Docker commit, which is the operation to turn a container into an image, or more realistically, Docker build, which will take a Docker file, so a recipe to build a container, and which will basically execute that recipe and create a new image for us.